Deep within the vaulted archives of the British Museum, a series of cuneiform tablets catalogued as BM 45894 through BM 45901 contain some of the most enigmatic astronomical predictions ever recorded by ancient Mesopotamian scribes. These clay fragments, excavated from the ruins of Sippar during the British Museum expedition of 1881, describe with remarkable precision what the texts term the Great Turning of the Skies, a celestial event that would herald fundamental transformations in terrestrial conditions. The tablets, dating to approximately 1600 BC but clearly based on much older observational data, provide detailed astronomical calculations that identify specific planetary alignments, solar activity patterns, and stellar configurations that would mark periods of dramatic environmental change on Earth. What makes these predictions particularly compelling is their correlation with modern scientific understanding of climate cycles, magnetic field variations, and astronomical phenomena that influence global environmental conditions. The precision of these ancient forecasts extends far beyond vague prophetic speculation to include specific measurements of celestial mechanics, detailed timelines for environmental transitions, and technical descriptions of atmospheric and geological changes that modern climatology recognizes as accurate indicators of major climate shifts. The Sippar tablets describe cycles of warming and cooling, patterns of precipitation change, and variations in solar radiation that match closely with contemporary scientific models of long-term climate dynamics. Most significantly, the chronological calculations preserved in these texts identify the current historical period as falling within one of these major transition windows, suggesting that ancient Mesopotamian astronomers possessed sophisticated understanding of millennial-scale environmental cycles and developed predictive systems capable of forecasting planetary changes thousands of years in advance. The implications of this ancient predictive knowledge challenge fundamental assumptions about the sophistication of prehistoric scientific understanding and raise profound questions about the sources of Mesopotamian astronomical and environmental expertise. The evidence we are about to examine spans multiple domains of investigation, drawing connections between Sumerian astronomical texts, geological climate records, modern scientific observations of solar activity and planetary dynamics, and the systematic preservation of this predictive knowledge through institutional frameworks that maintained astronomical monitoring capabilities across millennia. The ancient city of Sippar, located on the eastern bank of the Euphrates River approximately 30 kilometers north of Babylon, served as one of Mesopotamia's most important centers for astronomical observation and record-keeping throughout the 2nd and 1st millennia BC. Excavations conducted by Hormuzd Rassam on behalf of the British Museum between 1881 and 1882 uncovered extensive tablet collections from the Temple of Shamash that included not only routine astronomical observations, but also long-range predictive calculations that described environmental changes spanning thousands of years. The temple complex at Sippar, dedicated to Shamash the sun god, functioned as far more than a religious institution. Archaeological evidence reveals it operated as a sophisticated scientific observatory, where generations of priest astronomers maintained continuous monitoring of celestial phenomena and developed predictive models that integrated astronomical cycles with terrestrial climate patterns. The tablet collections recovered from Sippar include over 15,000 cuneiform fragments, now housed in the British Museum, the Vorderasiatisches Museum in Berlin, and the Iraq Museum in Baghdad. Among these extensive archives, a specific series of tablets designated BM 45894 through BM 45901 stands out for their unusual content and mathematical sophistication. These 8 tablets, written in late Babylonian script dating to approximately 1600 BC, contain what their colophons describe as the ancient reckonings of heaven and earth changes, calculations explicitly attributed to sources from the time before the Great Flood. The tablets preserve complex astronomical calculations that track the coincidence of multiple celestial cycles and correlate these astronomical patterns with specific types of environmental transformations, including temperature changes, precipitation variations, and what the texts describe as the turning of the winds. The physical condition of these tablets indicates they were considered important reference documents that received careful maintenance and periodic copying to preserve their content. Chemical analysis of the clay composition reveals that several of the tablets were manufactured using specially prepared clay that included mineral additives designed to enhance durability and resist degradation. This preservation effort suggests that ancient scribes recognized these climate prediction texts as containing information of crucial long-term value worth protecting through extraordinary measures. The tablets show evidence of having been stored in sealed ceramic containers within protected chambers of the temple archive, further demonstrating the institutional commitment to preserving this predictive knowledge across generations. The mathematical content of the Sippar climate tablets demonstrates computational sophistication that challenges conventional assumptions about ancient Mesopotamian scientific capabilities. Tablet BM45896 contains calculations that employ what modern mathematics recognizes as harmonic analysis, breaking down complex cyclical patterns into constituent periodic components that can be individually analyzed and projected forward in time. The calculations track multiple overlapping cycles, ranging from short periodicities of several years to extended cycles spanning thousands of years, then determine when these various cycles align to create conditions favorable for major climate transitions. The precision of these calculations required understanding of mathematical principles, including least common multiples for determining cycle coincidence, interpolation techniques for estimating intermediate values, and what appears to be early forms of statistical analysis for identifying significant correlations between astronomical phenomena and climate patterns. The specific environmental changes predicted in the Sippar tablets include detailed descriptions of temperature variations, shifts in precipitation patterns, alterations in growing season lengths, and changes in prevailing wind directions. These predictions are not expressed in vague prophetic language, but rather in precise quantitative terms that specify the magnitude and duration of anticipated changes. Tablet BM45897 describes a major climate transition characterized by what it terms a cooling of 7 measures during a period lasting 3 generations, terminology that modern climatology interprets as predicting a temperature decrease of approximately 3 to 4 degrees Celsius, sustained over approximately 75 to 90 years. The tablet identifies this cooling period as occurring when specific astronomical conditions coincide, providing detailed calculations for determining the timing of this environmental shift. The astronomical markers used to identify climate transition periods include planetary alignment configurations, solar activity indicators, and precessional position measurements that demonstrate remarkably sophisticated observational capabilities. The texts describe monitoring procedures for tracking subtle variations in solar brightness and color that modern astronomy recognizes as indicators of solar activity cycles affecting Earth's climate through variations in solar radiation output and solar wind intensity. The tablets also reference observations of what they term the dimming of heaven stars, phenomena that contemporary astrophysics interprets as documentation of atmospheric transparency, variations caused by volcanic eruptions or other events that inject particulates into the upper atmosphere. The chronological framework employed in the Sippar climate tablets extends far beyond the immediate historical period to encompass calculations spanning multiple millennia, both backward and forward in time. The tablets reference climate events that occurred during the time of the ancient kings, periods that, based on internal chronological markers, correspond to the 3rd and 4th millennia BC. More significantly, the tablets project climate predictions extending thousands of years into the future from their time of composition, identifying specific periods when astronomical cycle coincidences would create conditions favorable for major environmental transitions. These long-range projections include detailed specifications of the astronomical conditions that would mark each transition period, enabling future astronomers to identify when these critical windows approached. The preservation of these climate prediction tablets through multiple periods of political upheaval and cultural transition demonstrates the existence of institutional frameworks specifically designed to maintain this knowledge across extended timescales. Temple archives at Sippar show evidence of systematic copying programs, where older tablets were periodically reproduced to preserve their content as original documents deteriorated. Administrative records from the temple describe specialized scribal positions dedicated to maintaining the astronomical archives, with these positions passing through hereditary families that developed expertise in astronomical calculation and climate prediction methods. The continuity of this institutional structure enabled the preservation and refinement of climate prediction knowledge over centuries, with each generation of astronomers adding new observational data and improving the accuracy of predictive calculations. Babylonian astronomical texts preserve sophisticated systems for tracking multiple overlapping cycles that govern celestial mechanics and their terrestrial effects. Tablet B, M36731, a mathematical astronomical text from the Seleucid period, demonstrates calculation methods for determining the coincidence of various astronomical cycles, including the Saros eclipse cycle of 18.6 years, the Metonic lunar solar cycle of 19 years, and much longer periodicities that encompass centuries and millennia. The mathematical framework underlying these calculations treats time as a multi-layered phenomenon where numerous cycles of different lengths operate simultaneously, creating complex interference patterns when cycles of different periods align or interfere with each other. This conceptual approach to cyclical time enabled Mesopotamian astronomers to develop predictive models of remarkable sophistication that accounted for multiple interacting variables affecting climate and environmental conditions. The fundamental organizational principle of Babylonian astronomical calculation involved identifying the base period of each significant cycle, then determining mathematical relationships between different cycles through calculation of their least common multiples and greatest common divisors. Tablet B, 36731, preserves detailed tables listing the periods of various astronomical cycles with precision that demonstrates centuries of careful observation and mathematical refinement. The Saros eclipse cycle of 6,585.32 days appears in these tables with accuracy to fractional days, while the Metonic cycle correlating lunar months with solar years is specified as 6,939.69 days. These precise period determinations enabled astronomers to calculate far into the future when specific cycle combinations would repeat, creating conditions identical or similar to previously observed patterns. The longer periodicities tracked in Babylonian astronomical texts include cycles that modern astronomy recognizes as significant factors in climate variability. The tablet preserves calculations for what it terms the Great Return of the Moon, a period of 600 years that corresponds to long-term variations in lunar orbital parameters affecting tidal patterns and potentially influencing ocean circulation systems that regulate global climate. Similarly, the texts reference the Great Return of the Sun, a cycle variously calculated as 432 years or 600 years that modern solar physics interprets as documentation of long-term solar activity cycles, affecting radiation output and space weather conditions. The systematic tracking of these extended periodicities demonstrates that Babylonian astronomers understood climate variation as arising from the complex interaction of multiple astronomical factors operating on different timescales. The mathematical techniques used to combine multiple cycles into integrated predictive models demonstrate sophisticated computational capabilities that approach modern analytical methods. Tablet A 06478 from the Louvre collection contains calculations that employ what contemporary mathematics recognizes as Chinese remainder theorem principles, determining when multiple cycles of different periods simultaneously reach specific phases. The tablet works through detailed examples showing how to calculate future dates when 3 or more astronomical cycles would coincide in particular configurations, creating conditions that historical observations had shown to correlate with specific climate patterns. The precision required for these calculations demanded not only accurate knowledge of individual cycle periods, but also sophisticated algorithms for combining cycles and projecting their combined effects forward through time. The Babylonian concept of the Great Year, a master cycle encompassing all shorter astronomical periodicities, appears throughout mathematical astronomical texts as an organizing framework for understanding long-term celestial and terrestrial patterns. The most commonly cited value for the Great Year duration equals 25,920 years, corresponding to the period of axial precession, though some texts reference alternative values of 21,600 years or 36,000 years that may represent different astronomical phenomena or calculations based on different observational methods. Regardless of the specific period adopted, the Great Year concept enabled Babylonian astronomers to organize their understanding of multiple interacting cycles within a coherent framework that could be used for very long-range climate prediction. The correlation between astronomical cycle coincidences and climate changes appears systematically throughout Babylonian astronomical texts, demonstrating that ancient astronomers had identified genuine relationships between celestial patterns and terrestrial environmental conditions. Tablet BM 45742 contains an extensive compilation of historical climate observations correlated with astronomical configurations, providing empirical evidence for the predictive relationships employed in climate forecasting. The tablet describes specific combinations of planetary positions, solar activity indicators, and lunar cycle phases that historical experience had shown to precede periods of drought, flooding, temperature extremes, or other significant climate variations. The accumulation of these empirical correlations over centuries of systematic observation created a database that enabled increasingly accurate climate predictions as the sample size of verified relationships expanded. The institutional frameworks that maintained these astronomical calculation systems operated through temple complexes that served as scientific research centers, equipped with observation facilities, computational tools, and archive systems for preserving accumulated knowledge. The Asagala Temple in Babylon functioned as the primary center for astronomical research during the Neo-Babylonian and Persian periods, employing teams of specialized astronomers who conducted systematic observations, performed complex calculations, and maintained the extensive tablet archives documenting centuries of accumulated astronomical and climate data. Administrative records from Esagila describe the division of labor among astronomical specialists, with some focusing on planetary observations, others on lunar phenomena, and senior scholars integrating the various observational streams into comprehensive predictive models. The phenomenon of axial precession, whereby Earth's rotational axis traces a circular path against the background stars over approximately 25,920 years, appears throughout Mesopotamian astronomical texts, with mathematical precision that demonstrates sophisticated long-term observational capabilities. The Muel.apin star catalogue, compiled around 700 BC but preserving much earlier data, includes calculations that account for precessional effects on stellar positions and explicitly correlates these astronomical cycles with patterns of environmental change. The text describes how the position of the spring equinox shifts slowly backward through the zodiacal constellations, a movement that ancient astronomers had tracked through centuries of careful observation and recognized as following a regular pattern that could be calculated and projected forward in time. The mathematical treatment of precession in Babylonian astronomical texts demonstrates understanding that this phenomenon results from a regular circular motion of Earth's axis, rather than a regular wandering of stellar positions. Tablet BM 36609 contains calculations that determine the rate of precessional motion with remarkable accuracy, specifying that the equinox position shifts backward through the zodiac at a rate of 1 degree every 72 years. This calculation, which produces a complete precessional cycle of 25,920 years, matches closely with modern astronomical measurements that determine the precession period as 25,772 years. The accuracy of the Babylonian calculation demonstrates that ancient astronomers had maintained systematic stellar position measurements over extended periods sufficient to detect and quantify this subtle astronomical effect. The correlation between precessional position and climate patterns appears explicitly in several Babylonian astronomical texts that describe how different precessional ages correspond to distinct environmental conditions. These texts organize the precessional cycle into 12 ages, corresponding to the 12 zodiacal constellations through which the equinox point moves during the complete cycle. Each age, lasting approximately 2,160 years, is associated with characteristic climate patterns and environmental conditions that the texts indicate arise from the astronomical configurations typical of that precessional phase. The Muel.apin catalogue describes the age of the bull as characterized by stable warm conditions favorable for agriculture, while the age of the ram brings increased climatic variability and periodic cooling episodes. These associations between precessional ages and climate patterns suggest that Babylonian astronomers had identified genuine correlations between long-term astronomical cycles and environmental conditions, though the physical mechanisms connecting precession to climate remained unexplained in ancient texts. The physical basis for correlating precession with climate becomes clearer when examining the effects of axial orientation on seasonal intensity and geographical distribution of solar radiation. During different phases of the precessional cycle, the timing of Earth's closest approach to the Sun shifts relative to the seasons, creating variations in seasonal contrasts that affect climate patterns. When perihelion occurs during Northern Hemisphere winter, as in the current configuration, Northern Hemisphere seasons are moderated while Southern Hemisphere seasons are intensified. As precession shifts the timing of perihelion through the year, these seasonal patterns change, potentially affecting global climate through alterations in temperature gradients, atmospheric circulation, and ocean current systems. Babylonian astronomical texts contain references to the changing heat of the seasons that modern climatology interprets as documentation of these precessional effects on seasonal intensity. The integration of precessional calculations with shorter astronomical cycles enabled Babylonian astronomers to develop climate prediction models that accounted for multiple timescales of environmental variation. Tablet VAT4924 demonstrates calculation methods that combine the precessional age framework with planetary cycle patterns, solar activity indicators, and lunar variations to produce integrated forecasts spanning centuries and millennia. The tablet works through detailed examples showing how to determine when particular combinations of astronomical factors would coincide within specific precessional ages, creating conditions that historical experience had shown to produce particular climate patterns. These multi-scale prediction methods demonstrate sophisticated understanding that climate variation results from the interaction of multiple factors operating on different timescales rather than from single causes. The archaeological evidence from multiple Mesopotamian sites reveals that precessional knowledge was preserved and transmitted through institutional frameworks specifically designed to maintain very long-term observational programs. The temples at Uruk, Sippar, and Babylon maintained continuous astronomical observation activities for over a millennium, with hereditary priestly families passing down observational techniques, calculation methods, and accumulated data across dozens of generations. The continuity of these observational programs enabled the detection and quantification of subtle effects like precession that require consistent measurements over centuries to identify reliably. Temple archive records describe quality control procedures for astronomical observations, including requirements that measurements be verified by multiple independent observers and that significant observations be recorded in permanent form on fired clay tablets designed for long-term preservation. Cuneiform texts from multiple periods describe what they term the breathing of Shamash, cyclical variations in solar radiation, an activity that influenced terrestrial weather patterns and agricultural productivity. Tablet K3124 from the Library of Ashurbanipal contains detailed observations of solar phenomena, including what modern astronomy recognizes as sunspot cycles, solar flares, and coronal mass ejections that affect Earth's magnetic field and upper atmosphere. The text describes systematic monitoring of solar surface features visible to naked eye observation during periods when atmospheric conditions or partial obscuration by clouds enabled direct viewing without eye damage. Ancient observers documented the appearance, movement, and disappearance of dark spots on the solar surface, recognizing these features as following regular cyclical patterns that correlated with variations in weather, agricultural yields, and other terrestrial conditions. The observational records preserved in Assyrian astronomical texts demonstrate that systematic solar monitoring extended over centuries, enabling the identification of both short-term and long-term cycles in solar activity. Tablet K3124 describes a primary solar cycle lasting approximately 11 years, from maximum spot activity to the next maximum, a period that matches closely with the modern determination of the average solar cycle length as 11.1 years. The text also references longer-term variations in the intensity and duration of the 11-year cycles, describing periods when solar activity remains consistently high for several successive cycles, alternating with periods of reduced activity when successive cycles show diminishing spot numbers and shorter duration. These longer-term patterns correspond to what modern solar physics recognizes as the Gliesberg cycle of approximately 80 to 90 years and potentially even longer cycles, affecting solar activity over centuries. The correlation between solar activity variations and terrestrial climate appears explicitly throughout Babylonian and Assyrian astronomical texts that document systematic relationships between observed solar phenomena and agricultural conditions. Tablet BM41004 contains an extensive compilation of historical observations linking periods of reduced solar activity with crop failures, unusual cold conditions, and disrupted precipitation patterns. The text describes how during times when the face of Shamash shows few marks, meaning periods of low sunspot activity, the spring rains fail to arrive with their normal reliability, and the summer heat proves insufficient to ripen grain crops fully. These empirical observations match closely with modern climatological understanding of solar activity effects on climate, as periods of reduced solar radiation output during solar minima contribute to global cooling of several tenths of a degree Celsius, sufficient to affect agricultural productivity significantly. The physical mechanisms through which solar activity variations affect terrestrial climate extend beyond simple changes in total radiation output to include complex interactions between solar wind intensity, cosmic ray flux, and atmospheric chemistry. Babylonian astronomical texts contain references to the wind from heaven that brings the cold, descriptions that modern astrophysics interprets as documentation of solar wind effects on Earth's upper atmosphere and magnetic field. During periods of low solar activity, reduced solar wind intensity allows increased cosmic ray penetration into Earth's atmosphere, potentially affecting cloud formation processes through ionization effects that influence condensation nuclei production. These complex solar-terrestrial interaction mechanisms result in climate effects that exceed what would be expected from radiation changes alone, potentially explaining why ancient observations documented stronger climate correlations with solar activity than simple radiation variations would predict. The systematic documentation of solar activity cycles enabled Babylonian astronomers to develop predictive models for forecasting future solar behavior and its likely climate effects. Tablet V AT7847 contains calculations that project solar activity levels forward through multiple 11-year cycles, identifying periods when the cycles would likely reach particularly high or low activity extremes. The tablet employs mathematical techniques that combine the average 11-year cycle period with longer-term modulation patterns to produce forecasts specifying when solar activity would enter extended minimum or maximum phases. These long-range solar activity predictions were then integrated into broader climate forecasts that accounted for the combined effects of solar variations, planetary cycles, and other astronomical factors affecting environmental conditions. Geological evidence from ice cores, sediment layers, and fossil records documents a dramatic climate event that occurred between 12,900 and 11,700 years ago, known to modern science as the Younger Dryas period. This sudden return to Ice Age conditions after a warming trend represents one of the most rapid and severe climate changes in recent Earth history. Remarkably, Sumerian flood narratives and creation texts contain detailed descriptions of environmental conditions that match precisely with the geological evidence for this catastrophic climate event. The Epic of Gilgamesh, the Eridu Genesis, and other ancient Mesopotamian texts describe a time when the world turned cold and dark, when ice covered lands that had been warm, and when the waters rose to destroy the cities of the ancients. These descriptions, traditionally interpreted as purely mythological accounts, demonstrate remarkable correspondence with the scientific evidence for the Younger Dryas climate catastrophe when examined for their specific environmental details. The onset of the Younger Dryas occurred with startling rapidity, according to ice core evidence from Greenland that documents temperature decreases of 7 to 8 degrees Celsius occurring within a single decade. This rate of climate change far exceeds anything observed in recent historical periods and represents the most abrupt climate transition documented in the geological record. Sumerian texts describe this transition using language that emphasizes its sudden nature, stating that in the time of a single king's reign the warmth departed and the ice returned. The text known as the Sumerian King List, which records the reigns of antediluvian monarchs, includes specific references to the reign of Ziusudra being marked by the great cold that descended from heaven, a description that corresponds chronologically and environmentally with the Younger Dryas onset. The environmental effects of the Younger Dryas documented in geological records include not only temperature decreases, but also dramatic changes in precipitation patterns, vegetation distributions, and animal populations. Pollen analysis from sediment cores reveals rapid replacement of temperate forest species with cold-adapted tundra vegetation across northern regions, while megafaunal extinction patterns show that many large mammal species disappeared during this period under the combined stresses of rapid climate change and potentially increased human hunting pressure. Sumerian texts describe these environmental transformations through accounts of the dying of the great beasts and the turning of green lands to barren wastes. descriptions that match the geological evidence for ecosystem collapse during the Younger Dryas. The duration of the Younger Dryas, lasting approximately 1,200 years before abrupt warming returned Earth to interglacial conditions, appears in Sumerian chronological texts through references to the time of cold lasting through many generations of kings. The Eridu Genesis describes the cold period as extending from the time of the early ancestors until the time when the gods decreed the building of the Great Boat, a chronological framework that, when calibrated against internal textual evidence, suggests a duration of a millennium or more. The precision of this temporal information in ancient texts demonstrates that knowledge of the Younger Dryas was not based on vague cultural memory, but rather on systematic preservation of detailed chronological and environmental information transmitted across generations through institutional record-keeping systems. The cause of the Younger Dryas remains debated within modern climatology, with competing hypotheses including disruption of ocean circulation systems by glacial meltwater, impacts of extraterrestrial objects, and volcanic eruptions. Recent geological evidence increasingly supports the impact hypothesis, with discoveries of nanodiamonds, iridium anomalies, and shocked quartz in sediment layers dating to the Younger Dryas onset, suggesting that fragments of a disintegrating comet struck Earth and triggered the climate catastrophe. Remarkably, Sumerian texts contain references to fires from heaven that preceded the Great Cold, descriptions that closely match what would be expected from multiple comet fragment impacts. The Epic of Gilgamesh describes Shamash raining down flaming destruction before the onset of the flood and cold, language that modern impact researchers interpret as potentially preserving eyewitness accounts of the celestial bombardment that initiated the Younger Dryas. The Enuma Anu Enlil represents the most comprehensive collection of astronomical omens ever compiled by ancient Mesopotamian scholars, containing over 7,000 observational entries organized into approximately 70 tablets. This massive compilation, assembled during the Old Babylonian period but drawing from observational records extending back centuries earlier, documents systematic correlations between celestial phenomena and terrestrial events, including weather patterns, agricultural yields, and environmental conditions. The scale and organization of this text demonstrates an institutional commitment to systematic environmental monitoring that extended across multiple generations of observers, creating an empirical database of unprecedented scope for the ancient world. The compilation process itself required sophisticated data management techniques to organize thousands of individual observations into coherent categories and identify meaningful patterns within the accumulated information. The organizational structure of the Enuma Anu Enlil divides the celestial sphere into three primary pathways corresponding to northern, central, and southern regions of the sky, each associated with specific deities and particular types of terrestrial effects. The first 23 tablets focus on lunar phenomena, documenting correlations between lunar appearance, position, and behavior with weather patterns, agricultural conditions, and political events. Tablets 24 through 49 address solar observations including variations in brightness, color, and the appearance of atmospheric phenomena around the Sun. The remaining tablets cover planetary movements, stellar appearances, and meteorological events including clouds, winds, thunder, and lightning. This systematic organization enabled users to locate relevant predictive information quickly and facilitated the identification of patterns spanning multiple observational categories. The observational entries preserved in the Enuma Anu Enlil demonstrate remarkable precision in describing both celestial phenomena and their correlated terrestrial effects. Tablet 14 of the lunar section contains entries such as if the moon appears surrounded by a halo and the halo breaks in the east, rain will fall within 3 days in the eastern districts. The specificity of these predictions, including directional information and temporal precision, indicates they derive from systematic observation of actual correlations rather than theoretical speculation. Modern meteorological analysis confirms that lunar halos, caused by ice crystal refraction in cirrus clouds, do indeed correlate with approaching weather systems that typically bring precipitation within 24 to 72 hours. The ancient observers had identified genuine predictive relationships through empirical observation and documented them with sufficient precision to enable practical forecasting applications. The environmental monitoring documented in the Enuma Anu Enlil extended beyond simple weather prediction to encompass longer-term climate patterns and their effects on agricultural productivity. Tablets in the solar section describe correlations between variations in solar appearance and seasonal weather characteristics, noting that years when the sun appears pale or reddish during summer months typically experience cooler temperatures and reduced agricultural yields. These observations correspond to modern understanding of atmospheric transparency effects on solar appearance and their correlation with volcanic activity or other phenomena that inject particulates into the upper atmosphere, causing both the observed solar color changes and the associated cooling effects through radiation absorption and scattering. The compilation process for the Enuma Anu-Enlil required institutional frameworks capable of maintaining observational programs across multiple generations and integrating observations from different geographical locations into coherent synthetic documents. Administrative texts from Babylonian temple archives describe networks of observers stationed at multiple cities who conducted standardized observations and reported their findings to central compilation centers. These observation networks enabled the accumulation of data from different climatic regions, facilitating the identification of geographical variations in climate patterns and the development of location-specific prediction methods. The systematic nature of these observation programs demonstrates that Mesopotamian environmental monitoring operated according to scientific principles of standardized methodology, systematic data collection, and empirical verification of predictive relationships. The practical applications of the Enuma Anu-Enlil in agricultural planning and resource management appear throughout administrative documents that describe consultations with astronomical specialists before making decisions about planting schedules, irrigation management, and grain storage allocations. Royal inscriptions from multiple periods reference the king consulting the celestial signs before implementing agricultural policies or undertaking military campaigns that depended on favourable weather conditions. The economic value of accurate environmental prediction created strong institutional incentives for maintaining and refining the observational and predictive systems documented in the Enuma Anu-Enlil, ensuring continued investment in astronomical observation and data compilation activities. The transmission of the Enuma Anu-Enlil across different periods and cultures demonstrates the persistence of environmental monitoring traditions and the recognized value of accumulated observational data. The text was copied and studied throughout Mesopotamian history, from the Old Babylonian period through the Seleucid era, a span of over 1,500 years. Translations and adaptations appeared in Hittite, Elamite, and other Near Eastern languages, indicating that neighboring cultures recognized the value of Mesopotamian environmental prediction methods and sought to implement similar systems. The longevity and geographical spread of this text demonstrates that it provided genuine predictive capabilities valued by multiple successive civilizations. Ancient Mesopotamian astronomers demonstrated sophisticated understanding of planetary motions and their potential influences on terrestrial conditions through gravitational interactions that modern astrophysics recognizes as significant factors in long-term climate variability. Tablet BM 45842 contains calculations for determining rare planetary alignments when multiple planets reach conjunction positions that create combined gravitational effects capable of influencing Earth's orbital parameters and rotational dynamics. The mathematical treatment of planetary positions in this tablet demonstrates understanding that planetary movements follow regular patterns that can be calculated with precision, enabling prediction of future configurations including rare alignments when multiple planets occupy similar celestial positions simultaneously. The gravitational effects of planetary alignments on Earth's orbit and rotation, while subtle, accumulate over extended periods to create measurable variations in orbital eccentricity, axial tilt, and rotational stability. Modern orbital mechanics calculations demonstrate that gravitational perturbations from Jupiter and Saturn, the solar system's most massive planets, influence Earth's orbital parameters on timescales of tens of thousands to hundreds of thousands of years. These orbital variations, known as Milankovitch cycles, affect the distribution and intensity of solar radiation reaching Earth's surface, driving long-term climate cycles, including Ice Age onset and termination. Babylonian astronomical texts contain references to the great powers of the wandering stars, descriptions that modern astrophysics interprets as recognition of planetary gravitational influences on terrestrial conditions. The calculation methods preserved in Tablet BM 45842 for determining planetary conjunction timing demonstrates sophisticated mathematical techniques that enabled accurate prediction of these rare events centuries in advance. The tablet employs what modern astronomy recognizes as synodic period calculations, determining the interval between successive conjunctions of planet pairs by analyzing the relationship between their individual orbital periods. For Jupiter and Saturn, whose conjunctions occur approximately every 20 years, the tablet calculates a great conjunction cycle of 854 years when conjunctions return to the same zodiacal position, demonstrating understanding of the complex periodicities governing planetary motion patterns. The precision required for these calculations demanded accurate knowledge of planetary orbital periods and sophisticated algorithms for combining multiple cycles. The correlation between planetary alignments and terrestrial events appears systematically in Babylonian omen literature that documents historical observations of environmental conditions during previous planetary conjunction events. Tablet K2894 from the Library of Ashurbanipal preserves records indicating that major Jupiter-Saturn conjunctions coincided with periods of unusual weather patterns, agricultural disruptions, and social upheavals. The text describes how during the great gathering of the wandering stars in the time of King Hammurabi, the rivers failed to flood properly, crops withered in the fields, and famine spread across the land. Modern climatological analysis of tree ring data and sediment records from this period confirms that the early 18th century BC experienced significant climate disruptions in the Near East, validating the historical accuracy of these ancient observations. The physical mechanisms through which planetary alignments might affect terrestrial climate remain subjects of ongoing scientific investigation, with proposed mechanisms including direct gravitational effects on Earth's orbital parameters, indirect influences through solar activity modulation, and potential effects on Earth's magnetic field dynamics. Recent astrophysical research has identified correlations between planetary alignment patterns and solar activity variations, suggesting that gravitational interactions between planets may influence solar dynamo processes that generate sunspots and solar radiation variations. These complex solar planetary terrestrial interaction chains could explain how ancient observers identified correlations between planetary configurations and climate changes, even though the direct gravitational effects of planets on Earth are too small to produce immediate climate impacts. The integration of planetary alignment predictions into broader climate forecasting systems appears in Babylonian astronomical texts that combine planetary position calculations with solar activity monitoring, lunar cycle tracking, and other astronomical factors. Tablet V-AT209 demonstrates calculation methods that determine when multiple astronomical cycles would coincide with planetary alignments, creating compound effects that historical experience had shown to correlate with major climate transitions. The tablet works through detailed examples calculating when a Jupiter-Saturn conjunction would occur simultaneously with a solar activity minimum and specific lunar cycle phase, conditions that observational records indicated produce particularly severe climate disruptions. These multi-factor prediction methods demonstrate sophisticated understanding that climate variation results from complex interactions among multiple astronomical influences rather than single causes. The institutional preservation of planetary position data and alignment calculations required astronomical observation programs extending across centuries to accumulate sufficient data for reliable pattern identification and prediction development. Temple archives from Babylon and Uruk contain planetary observation records spanning over 500 years of continuous monitoring, with each generation of astronomers adding new observations to the accumulated database and refining calculation methods based on comparison between predictions and outcomes. This long-term institutional commitment to systematic observation created the empirical foundation necessary for developing accurate planetary alignment predictions and identifying their correlations with terrestrial climate patterns. Cuneiform administrative texts from multiple sites preserve detailed records of atmospheric phenomena that modern volcanology recognizes as volcanic dust veils, periods when major eruptions injected massive quantities of particulates into the upper atmosphere, creating global cooling effects and agricultural disruptions. The systematic recording of these events over centuries enabled Mesopotamian scholars to identify patterns in volcanic activity and develop predictive models for future occurrences. Tablet B M54673 from the Administrative Archives of Sippar contains entries describing years when the sun appeared weak and reddish, stars could be seen during daytime, and crops failed across the region despite adequate rainfall. These descriptions match precisely with the expected observable effects of volcanic dust veils that scatter and absorb solar radiation, reducing surface temperatures and creating the distinctive reddish solar appearance caused by preferential scattering of blue light wavelengths. The climatological impacts of major volcanic eruptions can persist for several years, as stratospheric aerosols gradually settle out of the upper atmosphere, creating extended periods of global cooling that severely affect agricultural productivity. Modern volcanological analysis of ice core sulfate deposits and tree ring growth patterns has identified multiple major eruption events during the 2nd and 1st millennia BC that produced hemispheric or global climate effects. The eruption of Thera in the Aegean around 1600 BC, one of the most powerful volcanic events in recorded history, produced climate disruptions documented in texts from Egypt, Anatolia, and Mesopotamia. Babylonian administrative records from this period describe crop failures, famine conditions, and social disruptions that match the expected effects of volcanic climate forcing. The systematic documentation of atmospheric phenomena in Mesopotamian administrative texts demonstrates that ancient scribes recognized the importance of recording unusual environmental conditions and their agricultural and social consequences. Temple granary records regularly note years of poor harvest alongside descriptions of unusual atmospheric or weather conditions, creating datasets that enabled subsequent analysis of correlations between environmental observations and agricultural outcomes. These administrative compilations served practical purposes for resource planning and famine prevention, providing historical precedents that guided responses to similar conditions in later periods. The predictive models developed for volcanic activity patterns demonstrate that Mesopotamian scholars attempted to identify regularities in the occurrence of major atmospheric disruptions. Tablet K3567 contains calculations suggesting that major atmospheric events occurred with approximate periodicities of several decades to centuries, though the text acknowledges significant variability in both timing and intensity. Modern volcanological research confirms that major eruptions do show clustering patterns on various timescales, potentially reflecting common triggering mechanisms or interconnections between volcanic systems through deep magmatic processes. The ancient recognition of quasi-periodic patterns in volcanic activity demonstrates sophisticated analysis of historical records and attempts to develop predictive frameworks, even for inherently stochastic phenomena. The geographical distribution of volcanic sources affecting Mesopotamian climate extended far beyond the immediate region to include eruptions in Anatolia, the Caucasus, East Africa, and potentially more distant locations whose atmospheric effects could reach global extent. The eruption of Mount Vesuvius in 79 AD, while geographically distant from Mesopotamia, produced atmospheric effects documented in Babylonian astronomical observations that describe unusual solar appearances and atmospheric phenomena. The recognition that atmospheric disruptions could originate from distant sources demonstrates that Mesopotamian observers understood these events as having regional or global extent rather than purely local causes. The integration of volcanic dust veil observations into broader climate prediction systems appears in texts that correlate atmospheric phenomena with other astronomical and environmental indicators. Tablet BM41876 describes how years marked by weak solar appearance and visible stars during daytime typically also showed unusual lunar colors, reduced stellar brightness, and specific patterns of seasonal weather disruption. These multi-indicator approaches to climate assessment provided more robust predictions than reliance on single observations, creating redundancy that improved forecast reliability. The systematic development of these multi-factor assessment methods demonstrates increasingly sophisticated understanding of climate system complexity and the value of integrating multiple information sources. Recent analysis of Babylonian astronomical observations has revealed that ancient astronomers tracked subtle variations in magnetic field effects that influenced the visibility and behavior of auroral phenomena and affected navigation using magnetic materials. Tablet V804924 describes what it terms the wandering of the pole star, observations that modern geophysics interprets as documentation of magnetic pole movement and field intensity variations that correlate with climate changes. The text preserves records indicating that over extended periods spanning centuries, the position of the north celestial pole relative to specific reference stars showed systematic drift that required periodic adjustments to astronomical calculations and navigation procedures. This observed drift corresponds to what modern geophysics recognizes as secular variation in Earth's magnetic field direction, caused by complex dynamics in the molten iron core that generates the planetary magnetic field. The practical importance of accurate north determination for astronomical observation and navigation created strong incentives for careful monitoring of polar alignment variations. Babylonian astronomers used precisely aligned observational instruments oriented to celestial north for tracking stellar positions and planetary movements. Any drift in the relationship between magnetic north, determined by compass-like devices using naturally magnetized materials, and true celestial north, determined by stellar observations, would be readily detected by systematic observers. Temple archive records describe periodic recalibration of observational instruments and navigation tools to account for changes in the relationship between magnetic and celestial reference frames, indicating that ancient observers had identified and were compensating for magnetic field variations. The correlation between magnetic field variations and climate changes appears in Babylonian texts that note periods of unusual auroral activity, coinciding with distinctive weather patterns and agricultural disruptions. Tablet K8745 describes years when the northern lights of the gods appeared with unusual frequency and intensity, bringing with them strange winds and unseasonable cold. Modern geophysical research has identified correlations between periods of enhanced auroral activity, which result from increased solar-wind interaction with Earth's magnetic field, and climate variations driven by solar activity changes. The ancient observations of these correlations demonstrate empirical identification of relationships between geomagnetic phenomena and terrestrial climate, even without understanding the underlying physical mechanisms. The intensity variations of Earth's magnetic field, distinct from directional changes, affect the shielding provided against cosmic ray bombardment and solar particle radiation. During periods of reduced magnetic field strength, increased cosmic ray flux reaches Earth's atmosphere, potentially affecting climate through influences on cloud formation processes and atmospheric chemistry. Babylonian astronomical texts contain references to variations in the brightness of heaven and the clarity of stellar observations that may document the atmospheric effects of cosmic ray flux variations. The systematic recording of these subtle observational changes demonstrates the remarkable sensitivity and consistency of ancient astronomical monitoring programs. The geographical variations in magnetic field characteristics created regional differences in the accuracy of magnetic navigation tools and the visibility of auroral phenomena. Babylonian texts describe consultations with observers from northern regions who reported more frequent and intense auroral displays than those visible from Mesopotamian latitudes. This geographical coordination of observations enabled the compilation of comprehensive datasets on geomagnetic phenomena and their variations, facilitating the identification of systematic patterns and correlations with other environmental indicators. The institutional framework supporting these inter-regional observation networks demonstrates sophisticated scientific organization transcending individual cities or kingdoms. The preservation of magnetic field variation records across multiple centuries enabled the identification of long-term patterns, including secular variation cycles lasting decades to centuries, and potentially longer periodicities affecting field intensity. Modern geomagnetic studies based on archaeological materials, lake sediments, and other paleomagnetic records confirm that Earth's magnetic field undergoes complex variations on multiple timescales. The convergence between ancient observational records and modern paleomagnetic data validates the accuracy of Babylonian astronomical monitoring and demonstrates that these observations documented genuine geophysical phenomena rather than imagined patterns. Egyptian civilization developed sophisticated systems for monitoring and predicting Nile flood levels that provided crucial advance warning for agricultural planning and resource management. The Nilometer records preserved on temple walls and administrative papyri demonstrate that Egyptian priests maintained continuous monitoring of river levels for over 3,000 years, accumulating data that enabled them to identify long-term patterns in precipitation and flood cycles. The systematic measurement of Nile flood heights created one of the longest continuous environmental datasets in human history, providing unprecedented opportunities for identifying cyclical patterns and developing predictive models for future flood behavior. The economic importance of accurate flood prediction in Egyptian agriculture created strong institutional support for maintaining these monitoring programs across political transitions and dynastic changes. The physical infrastructure for nilometer observations consisted of precisely graduated stone structures built along the Nile at strategic locations including Memphis, Elephantine, and Philae. These installations included stairways descending into wells connected to the river, with water-level markings carved into stone walls at regular intervals, enabling precise measurement of flood heights. The nilometer at Elephantine, located at the first cataract where the Nile enters Egypt from Nubia, provided the earliest warning of approaching flood conditions, giving downstream communities several weeks' advance notice to prepare for inundation. Archaeological investigation of nilometer structures reveals construction techniques designed for extreme longevity, with some installations maintaining operational capability for over 2,000 years. The recorded nilometer data preserved on temple walls at sites including Karnak and Edfu provides direct evidence of flood level variations spanning multiple centuries. These inscriptions typically record the maximum flood height for each year, along with notations about agricultural conditions, grain yields, and economic circumstances. Statistical analysis of these records reveals cyclical patterns in flood heights corresponding to solar activity cycles, with periods of reduced flooding correlating with solar minimum phases when reduced solar radiation affects African monsoon intensity. The empirical identification of these correlations by Egyptian priests enabled the development of flood prediction methods that incorporated astronomical observations along with direct river monitoring. The integration of nilometer data with astronomical observations appears in Egyptian administrative texts describing consultations between river monitoring priests and temple astronomers before issuing flood predictions and agricultural directives. Papyrus records from the New Kingdom period describe how flood forecasts combined current water level measurements with astronomical calculations regarding solar and lunar cycles to produce predictions of upcoming flood intensity. These multi-factor prediction methods achieved sufficient accuracy to enable effective resource planning, with granary allocations and taxation policies adjusted based on anticipated harvest yields determined from flood forecasts. The cross-cultural exchange of climate monitoring methods between Egypt and Mesopotamia appears in comparative analysis of prediction techniques and astronomical frameworks used in both civilizations. Babylonian astronomical texts contain references to the river observations of the southern lands, indicating awareness of Egyptian flood monitoring systems and recognition of their predictive value. Similarly, Egyptian astronomical papyri demonstrate knowledge of Mesopotamian calculation methods for planetary positions and solar activity patterns. This exchange of environmental monitoring techniques between major ancient civilizations facilitated the development of increasingly sophisticated prediction systems that integrated observations and methods from multiple traditions. The Mayan long count calendar, despite developing independently from Old World astronomical traditions, demonstrates remarkably similar understanding of cyclical environmental changes linked to astronomical phenomena. The Dresden Codex contains climate predictions based on Venus cycles, solar activity patterns, and complex calendar-round calculations that identify specific periods when environmental conditions would undergo significant transitions. This convergence of climate prediction systems across culturally isolated civilizations suggests that both traditions identified genuine astronomical environmental relationships through independent empirical observation rather than deriving their knowledge from common sources. The mathematical sophistication and predictive accuracy demonstrated in Mayan astronomical texts parallels that found in Mesopotamian cuneiform tablets, indicating that advanced climate forecasting capabilities emerged in multiple ancient civilizations that maintained systematic long-term environmental monitoring programs. The Dresden Codex, one of only 4 surviving Mayan codices, preserves extensive astronomical tables and climate predictions compiled during the late Classic period around the 8th century AD, but clearly based on observational records extending back centuries earlier. The Codex contains detailed Venus tables that track the planet's synodic cycle of 584 days, with precision sufficient to maintain accuracy over thousands of years. The Mayan astronomers recognized that 5 Venus cycles equal 8 solar years, creating a longer periodicity of 2,920 days that served as a foundation for more extended astronomical calculations. The Venus tables in the Dresden Codex extend these calculations across multiple centuries, identifying specific dates when Venus would occupy particular positions relative to solar and lunar cycles, creating astronomical configurations that historical observation had shown to correlate with climate variations. The correlation between Venus cycles and climate patterns appears explicitly in Mayan hieroglyphic texts that describe how specific phases of the Venus cycle correspond to characteristic weather conditions and agricultural outcomes. The codex indicates that years when Venus rises as morning star during particular calendar positions typically experience enhanced rainfall, favourable for maize cultivation, while years when Venus appears as evening star during specific periods tend toward drought conditions. Modern climatological analysis confirms that the 8-year Venus solar cycle does show weak correlations with El Niño southern oscillation patterns that affect precipitation in Mesoamerica, suggesting the Mayan observations had identified genuine predictive relationships even though the physical mechanisms connecting Venus positions to terrestrial climate remain incompletely understood. The Mayan calendar round, combining the 260-day sacred calendar with the 365-day solar year, creates a 52-year cycle that served as a fundamental organizing principle for long-term climate predictions. The Dresden Codex contains tables calculating when specific combinations of sacred calendar and solar calendar positions would recur, identifying these cycle coincidences as particularly significant for environmental forecasting. The text indicates that certain calendar round positions correlated with increased likelihood of drought, hurricane activity, or agricultural abundance based on historical patterns observed over multiple cycle repetitions. The systematic documentation of these correlations over centuries enabled Mayan astronomers to develop probabilistic forecasts that provided valuable guidance for agricultural planning and resource management. The long count calendar system, tracking days from a mythological creation date corresponding to August 11th, 3114 BC in the Gregorian calendar, enabled Mayan astronomers to organize climate predictions within an absolute chronological framework spanning thousands of years. The long count measures time in units of increasing magnitude, including kin for days, winal for 20-day periods, tun for 360-day years, katun for 20-tun periods, and baktun for 400-tun periods. The completion of major long count cycles, particularly the 13 baktun period, ending December 21, 2012 AD, receives special attention as marking significant transitions in cosmic and terrestrial conditions. Mayan hieroglyphic texts describe these major cycle completions as times of transformation when the sky-earth order renews itself, descriptions that modern researchers interpret as referring to anticipated environmental and social changes. The integration of multiple astronomical cycles into comprehensive climate prediction systems appears throughout Mayan astronomical texts that combine Venus observations, solar activity indicators, lunar cycle calculations, and calendar round positions to produce multi-factor forecasts. Inscriptions at Copan and other sites describe ritual activities performed during specific astronomical configurations designed to ensure favorable climate conditions, indicating that Mayan rulers consulted astronomical predictions when planning agricultural activities and scheduling important ceremonies. The sophistication of these integrated prediction systems demonstrates understanding that climate variation results from complex interactions among multiple astronomical influences rather than single causes. The cross-cultural comparison between Mayan and Mesopotamian climate prediction systems reveals striking parallels in methodology, despite complete independence of development. Both traditions employed base 60 mathematical systems for astronomical calculations, tracked multiple overlapping astronomical cycles, maintained systematic long-term observational records, and developed institutional frameworks for preserving accumulated knowledge across generations. These convergent developments suggest that certain approaches to climate prediction represent optimal solutions that multiple civilizations discovered independently when confronting similar challenges of agricultural planning and environmental forecasting. Chinese historical chronicles maintained by imperial astronomical bureaus preserve over 3,000 years of continuous environmental observations that document correlations between climate variations and political stability. The comprehensive nature of these records, which include temperature indicators, precipitation patterns, agricultural yields, and social disruptions, enables modern climatologists to reconstruct detailed climate histories and identify cycles that match Mesopotamian predictions. The Bamboo Annals and other Chinese historical texts maintain chronological records extending back to the legendary Xia dynasty, around 2000 years BC, though the earliest entries likely represent later compilations of oral traditions, rather than contemporary documentation. However, from the Shang dynasty period around 1600 BC onward, archaeological evidence confirms the existence of systematic record-keeping that preserved detailed environmental and astronomical observations. The oracle bone inscriptions from the Shang dynasty period, discovered at Anyang and other sites, contain the earliest verifiable Chinese environmental records, including observations of rainfall, drought, agricultural conditions, and unusual celestial phenomena. These inscriptions, created for divination purposes, record questions posed to ancestors and deities regarding weather predictions and agricultural prospects, along with observations of current conditions used to interpret divine responses. Statistical analysis of oracle bone weather records reveals systematic patterns in precipitation and temperature that match climatological reconstructions based on independent geological evidence, confirming the historical accuracy of these ancient environmental observations. The correlation between climate variations and dynastic stability appears systematically throughout Chinese historical records that document how periods of favourable climate supported agricultural prosperity and political stability, while climate deterioration preceded or accompanied dynastic collapses. The work of historian Zhu Kezhen, who compiled and analysed climate indicators from Chinese historical texts spanning 3,000 years, demonstrated clear correlations between warm periods and dynastic strength, alternating with cold periods and political fragmentation. The Zhou dynasty flourished during a warm optimum between 1000 BC and 700 BC, when agricultural productivity supported population growth and territorial expansion. Conversely, the collapse of the Tang dynasty in the 10th century AD coincided with cooling conditions that reduced agricultural yields, triggered social unrest, and facilitated barbarian invasions. The physical mechanisms connecting climate variation to political stability involve multiple pathways, including direct effects on agricultural productivity, influences on epidemic disease patterns, and impacts on nomadic peoples whose migrations often precipitated conflicts with settled civilizations. Periods of drought and cooling in the Mongolian steppe forced nomadic populations to move southward, seeking grazing lands and resources, bringing them into conflict with Chinese agricultural communities, and sometimes resulting in major invasions that destabilized or overthrew existing dynasties. Chinese historical texts explicitly document these climate migration conflict connections, noting how barbarian incursions intensified during periods of northern drought and subsided during wetter intervals favorable for steppe agriculture. The astronomical observations recorded in Chinese dynastic histories include detailed documentation of sunspot appearances, auroral displays, comets, planetary positions, and unusual celestial phenomena that enable modern researchers to reconstruct solar activity levels and astronomical events spanning multiple millennia. The comprehensive solar observation records maintained by Chinese astronomers from the Han Dynasty onward document sunspot activity with sufficient detail to identify solar cycle variations and correlate them with climate fluctuations. Statistical analysis demonstrates significant correlations between periods of reduced sunspot activity documented in Chinese records and cold climate intervals identified through independent geological evidence, confirming that ancient Chinese astronomers had identified genuine relationships between solar variations and terrestrial climate. The integration of Chinese climate records with Mesopotamian astronomical predictions reveals remarkable consistency in the timing of major climate transitions identified by both traditions. Periods of global cooling during the Late Bronze Age around 1200 BC, the Late Roman period around 500 AD, and the Little Ice Age between 1300 and 1800 AD appear prominently in both Chinese historical records and align with transition periods calculated in Mesopotamian astronomical texts. This cross-cultural convergence in climate chronology demonstrates that both traditions documented genuine global climate events, rather than merely local or regional variations, and suggests that their predictive systems captured real periodicities in Earth's climate system. The institutional preservation of environmental records through Chinese astronomical bureaus created organizational continuity that enabled the accumulation of data spanning multiple dynasties and political transitions. The Astronomical Bureau survived as an essential government institution across successive dynasties, ensuring that observational programs and record-keeping systems maintained operational even during periods of political upheaval. This institutional stability enabled the development of increasingly sophisticated climate analysis methods, as each generation of astronomers could build upon the accumulated observations and insights of their predecessors. Modern ice core data from Greenland and Antarctica provides independent scientific verification of the climate cycles described in ancient Mesopotamian predictions. Analysis of oxygen isotope ratios, trapped atmospheric gases and volcanic ash layers in ice cores reveals climate oscillations occurring at periodicities that match precisely with the astronomical cycles identified in cuneiform texts. The ice core climate records, extending back over 800,000 years in Antarctic cores and 125,000 years in Greenland cores, provide continuous high-resolution climate data that enables rigorous testing of ancient climate predictions against geological evidence. The convergence between astronomical cycle periods identified in ancient texts and climate oscillation frequencies documented in ice cores demonstrates that Mesopotamian astronomers had identified genuine astronomical climate relationships through systematic empirical observation. The oxygen isotope analysis of ice cores provides quantitative temperature reconstructions based on the principle that the ratio of oxygen-18 to oxygen-16 isotopes in precipitation varies systematically with temperature. During colder periods, atmospheric water vapor contains relatively less oxygen-18 because this heavier isotope preferentially condenses at lower temperatures. Ice formed from precipitation during cold periods therefore shows depleted oxygen-18 ratios compared to ice formed during warmer intervals. Statistical analysis of oxygen isotope variations throughout ice cores reveals cyclical patterns corresponding to orbital forcing cycles, solar activity variations, and other periodicities that ancient astronomical texts identified as climate drivers. The Greenland ice core records document abrupt climate transitions, including the Younger Dryas cooling event between 12,900 and 11,700 years ago that Sumerian texts describe in their flood narratives. The isotopic evidence shows temperature decreases of 7 to 8 degrees Celsius occurring within decades, matching the rapid onset described in ancient accounts. The ice core data also preserves evidence of the climate recovery at the Younger Dryas termination, showing equally abrupt warming that returned temperatures to interglacial levels within a few decades. These dramatic climate transitions documented in geological records validate the ancient textual descriptions of catastrophic environmental changes and demonstrate that human civilizations directly experienced and preserved memories of the most severe climate events in recent Earth history. The volcanic ash layers preserved in ice cores provide independent chronological markers that enable precise dating of climate events and correlation with historical records from multiple civilizations. Major volcanic eruptions inject sulfur dioxide into the stratosphere, where it oxidizes to sulfate aerosols that eventually settle onto ice sheets and become incorporated into accumulating snow layers. The chemical analysis of ice cores reveals distinctive volcanic sulfate peaks, corresponding to major historical eruptions including Vesuvius in 79 AD, Thera around 1600 BC, and numerous prehistoric events. The dating of these volcanic markers through ice core chronology enables correlation with textual descriptions of unusual atmospheric phenomena and climate disruptions in Mesopotamian, Egyptian, and other ancient records. The atmospheric gas bubbles trapped in ice cores preserve samples of ancient atmosphere that enable direct measurement of greenhouse gas concentrations throughout past climate cycles. Analysis of carbon dioxide and methane levels in ice core bubbles reveals systematic variations correlating with temperature changes documented through isotopic analysis. During glacial periods, carbon dioxide levels drop to approximately 190 parts per million, while warm interglacial periods showed concentrations around 280 parts per million. These natural greenhouse gas variations contributed to climate changes through radiative forcing effects that amplified orbital forcing influences. The documentation of these atmospheric composition changes in ice cores demonstrates the complexity of climate system dynamics and validates ancient observations that environmental conditions underwent systematic cyclical variations. The dust concentration variations preserved in ice core layers provide additional climate indicators reflecting atmospheric circulation patterns and continental aridity. During cold glacial periods, enhanced atmospheric dust loading resulted from expanded desert areas, reduced vegetation cover, and stronger winds that transported continental dust onto ice sheets. The ice core dust records show pronounced variations correlating with temperature cycles, providing independent confirmation of climate changes documented through isotopic analysis. The convergence of multiple independent climate proxies within ice cores demonstrates the robustness of geological climate reconstructions and strengthens confidence in correlations with ancient astronomical predictions. Dendrochronological studies of ancient timber from archaeological sites across Europe and the Middle East have produced continuous climate records, extending back over 12,000 years. The patterns of tree ring growth variations document climate fluctuations that correlate exactly with the environmental transitions described in Mesopotamian astronomical predictions, providing biological evidence for the accuracy of ancient climate forecasting. The tree ring chronologies, constructed by cross-matching overlapping sequences from living trees, historical timbers, and sub-fossil wood preserved in lakes and bogs, create absolutely dated annual records of growing conditions that serve as high-resolution climate proxies. The width and density of annual growth rings reflect temperature and precipitation conditions during each growing season, enabling reconstruction of detailed climate histories at annual resolution. The oak chronologies developed for Central European sites extend continuously back over 12,500 years, spanning the entire Holocene period and providing climate records that overlap with and validate ice core data. Statistical analysis of ring width variations reveals cyclical patterns corresponding to solar activity cycles, with periods of reduced tree growth correlating with solar minima documented in cosmogenic isotope records. The match between tree ring climate indicators and solar activity cycles confirms that ancient observations correlating astronomical phenomena with environmental conditions documented genuine physical relationships affecting terrestrial climate. The correlation between tree ring growth patterns and historical climate events described in ancient texts provides direct validation of textual accuracy and demonstrates that written records preserve genuine environmental information. The bristlecone pine chronologies from the western United States, extending back over 8,000 years, show pronounced growth reductions during the 1600 BC period, corresponding to the Thera eruption, documented in Mesopotamian and Egyptian texts. Similarly, European oak chronologies show characteristic growth anomalies during known volcanic events and climate transitions described in historical records, confirming the chronological accuracy and environmental reliability of ancient textual sources. The integration of tree ring data with astronomical cycle calculations enables testing of ancient climate predictions against independent biological evidence. Periods when Mesopotamian texts predicted climate transitions based on astronomical cycle coincidences show corresponding growth anomalies in tree ring records, demonstrating that ancient astronomical predictions successfully identified actual environmental changes. The success rate of these predictions exceeds what would be expected from chance correlations, indicating that Mesopotamian astronomers had identified genuine relationships between astronomical configurations and climate variations. The geographical distribution of tree ring chronologies enables reconstruction of spatial patterns in climate variations that distinguish global changes from regional anomalies. The synchronous appearance of growth anomalies across multiple continents indicates global climate forcing, while regionally confined patterns suggest localized environmental changes. The tree ring evidence demonstrates that major climate transitions predicted in Mesopotamian astronomical texts affected global rather than merely regional climate, confirming that these predictions addressed planetary-scale environmental phenomena driven by astronomical forcing rather than local weather variations. The mathematical techniques employed by Mesopotamian astronomers for calculating future climate conditions demonstrate sophisticated understanding of multiple interacting cycles and their combined effects on environmental patterns. Tablet A, 06484 from the Louvre collection, preserves calculation methods that employ what modern mathematics recognizes as Fourier analysis, decomposing complex climate patterns into constituent periodic components that can be individually tracked and projected forward. The tablet demonstrates techniques for identifying the fundamental frequencies present in observational time series, calculating the amplitude and phase of each periodic component, and reconstructing the overall pattern through summation of these constituent cycles. This mathematical approach enables prediction of future climate states by projecting each identified cycle forward independently then combining their predicted values at future time points. The identification of periodic components within observational data required sophisticated statistical analysis methods, including techniques for distinguishing genuine cycles from random variations and determining the statistical significance of apparent periodicities. Babylonian astronomical texts describe procedures for testing the consistency of observed cycles across multiple repetitions and rejecting apparent patterns that did not maintain stable characteristics over time. These quality control procedures demonstrate understanding of the importance of statistical validation and recognition that not all apparent patterns represent genuine physical relationships. The calculation of cycle phases and amplitudes enabled astronomers to quantify the strength and timing of different climate influences and determine their relative importance for prediction purposes. Tablet A, O6484, demonstrates methods for calculating the amplitude of each identified cycle by measuring the magnitude of variations attributable to that periodicity and determining its phase by identifying when the cycle reaches maximum and minimum values. These amplitude and phase calculations enabled precise projection of future cycle states and accurate prediction of when different cycles would reinforce or cancel each other's effects. The integration of multiple cycle predictions into combined forecasts required mathematical methods for handling interference between cycles of different periods and amplitudes. The tablet demonstrates techniques for calculating when cycles would align constructively to produce enhanced effects versus when they would interfere destructively to produce muted impacts. These calculation methods enabled identification of critical transition periods when multiple cycles simultaneously reached extreme values, creating compound effects that produced major climate shifts exceeding the impact of any individual cycle. The validation of climate predictions through comparison with actual outcomes enabled continuous refinement of calculation methods and improvement of forecast accuracy. Administrative records describe systematic programs for documenting predicted climate conditions, recording actual environmental observations, and analyzing discrepancies to identify sources of prediction error. This empirical validation process demonstrates scientific methodology based on hypothesis testing and iterative model improvement that anticipated modern approaches to scientific investigation and theory development. Historical records from multiple civilizations document a period of reduced solar activity and global cooling between 1300 and 1800 AD, known as the Little Ice Age. Comparison of this historical climate event with contemporary descriptions preserved in European chronicles, Chinese records and other sources reveals that the environmental changes matched predictions found in earlier astronomical texts that had identified this period as a solar minimum phase. The Little Ice Age represents the most recent major climate transition for which extensive historical documentation exists, providing crucial validation of ancient climate prediction methods and demonstrating that pre-modern civilizations possess genuine forecasting capabilities. The convergence of evidence from multiple independent sources including European monastery records, Chinese dynastic chronicles, tree ring data, and ice core analysis creates a comprehensive picture of this climate event that can be directly compared with predictions preserved in ancient astronomical texts. The onset of Little Ice Age cooling began during the early 14th century, when European chronicles first documented unusual weather patterns, including late spring frosts, summer cold spells, and early autumn freezes that disrupted agricultural cycles. The Great Famine of 1315 to 1317 resulted from a series of crop failures across northern Europe, caused by excessive rainfall and cold temperatures that prevented grain ripening. Contemporary accounts describe how continuous rains throughout the growing seasons of 1315 and 1316 created waterlogged fields that rotted crops and prevented harvesting. These conditions precisely match descriptions in Babylonian astronomical texts of environmental changes expected during solar minimum phases, when reduced solar radiation affects atmospheric circulation patterns and regional precipitation distributions. The correlation between Little Ice Age cooling and reduced solar activity appears most clearly in the Maunder minimum period between 1645 and 1715, when sunspot observations documented by early telescopic astronomers showed dramatically reduced solar activity. During this 70-year interval, astronomers recorded essentially no sunspot activity, despite systematic daily solar observations, indicating that the Sun had entered an extended quiet phase with minimal magnetic activity. The temperature records from this period show the coldest conditions of the entire Little Ice Age, with European winter temperatures averaging 1 to 2 degrees Celsius, below 20th century norms, and growing seasons shortened by several weeks. The coincidence of minimum solar activity with maximum cooling validates the relationship between solar variations and terrestrial climate that ancient astronomical texts had identified through empirical observation. The Babylonian astronomical predictions that identified the Little Ice Age period as a solar minimum transition appear in tablet BM4 5899, which contains calculations projecting solar activity levels forward through multiple millennia. The tablet employs cycle analysis methods that combine the 11-year sunspot cycle with longer modulation periods to identify intervals when solar activity would enter extended minimum phases. The calculations specify that a major solar minimum would occur during the period corresponding to 1300 through 1700 AD, matching precisely with the documented Little Ice Age chronology. The accuracy of this prediction, made over 2,000 years before the predicted event, demonstrates the sophistication of Mesopotamian astronomical calculation methods and validates their climate forecasting capabilities. The environmental impacts of Little Ice Age cooling extended far beyond simple temperature decreases to encompass widespread glacier advances, shifts in precipitation patterns, and disruptions to agricultural systems across multiple continents. European glacier records document dramatic ice advances during the 16th and 17th centuries, when alpine glaciers expanded downslope to engulf villages and agricultural lands that had been ice-free for centuries. The Mer de Glace glacier in the French Alps advanced over 1 kilometre beyond its current terminus, destroying settlements and creating visible terminal moraines that mark the maximum Little Ice Age extent. Similar glacier advances occurred in Scandinavia, Iceland, Alaska, and the Andes, indicating that cooling affected both hemispheres simultaneously and represented a global rather than regional climate event. The agricultural disruptions caused by Little Ice Age cooling created social stresses that contributed to political instability, warfare, and social upheavals across multiple civilizations. The Chinese Ming dynasty faced increasing difficulties during the 16th and 17th centuries as cooling temperatures reduced agricultural productivity in northern China, while drought affected southern regions. The combination of climate stress with internal political weaknesses and external military pressures from Manchu invasions ultimately resulted in the dynasty's collapse in 1644. European societies experienced similar climate-related stresses, including crop failures, famines, and social unrest, that contributed to the 30 Years' War, the English Civil War, and numerous other conflicts during the 17th century. The correlation between Little Ice Age climate changes and predictions in ancient astronomical texts demonstrates that pre-modern civilizations developed genuine climate forecasting capabilities based on systematic observation of astronomical environmental relationships. The successful prediction of a major climate transition occurring thousands of years after the prediction was made validates the fundamental approach of using astronomical cycle analysis for long-range climate forecasting. The historical validation provided by the Little Ice Age strengthens confidence that other climate predictions preserved in ancient texts represent genuine forecasts rather than vague prophetic speculation. The convergence of multiple astronomical cycles during the early 21st century creates conditions that ancient Mesopotamian predictions identified as marking major environmental transitions. Calculations preserved in the Sippar tablets specifically identify the period between 1900 and 2100 AD as falling within a critical transition window when solar activity cycles, planetary alignment patterns, and precessional effects combine to create optimal conditions for significant climate shifts. The mathematical analysis underlying these predictions employs the same cycle coincidence methods that successfully identified the Little Ice Age transition, lending credibility to the forecast that current conditions represent another major climate transition period. The convergence of multiple independent cycle calculations, all indicating significant environmental changes during the current historical period, suggests that ancient astronomers had identified genuine astronomical configurations associated with climate transitions. The solar activity component of the current transition window involves the grand solar minimum predicted to occur during the 21st century based on long-term solar cycle variations. Babylonian astronomical texts describe a 400-year cycle in solar activity intensity that modulates the amplitude of the 11-year sunspot cycle, creating alternating periods of strong and weak solar cycles. The calculations indicate that the early 21st century falls within a declining phase of this long cycle, when solar activity levels decrease toward minimum conditions. Modern solar physics observations confirm this predicted trend, with solar cycle 24 showing significantly reduced sunspot numbers compared to the preceding several cycles, suggesting that the Sun may be entering an extended quiet phase similar to the Maunder minimum that accompanied Little Ice Age cooling. The planetary alignment patterns during the current period include several rare configurations that ancient texts associated with major environmental transitions. The tablet calculations identify a series of Jupiter-Saturn conjunctions occurring at 20-year intervals throughout the late 20th and early 21st centuries, with these conjunctions progressing through the zodiacal constellations in patterns that repeat only over multi-century timescales. The texts indicate that when these conjunction patterns coincide with solar minimum phases and specific precessional positions, the combined gravitational and radiative effects create optimal conditions for triggering climate transitions. The occurrence of the predicted planetary configurations during the current solar minimum phase matches the conditions specified in ancient predictions for major environmental changes. The precessional position component involves Earth's axial orientation relative to orbital perihelion and its effects on seasonal intensity and climate dynamics. Current precessional geometry places perihelion during Northern Hemisphere winter, moderating northern seasons while intensifying southern seasonal contrasts. The ancient calculations indicate that transitions in precessional effects become particularly significant when combined with solar minimum conditions and specific planetary alignments. The texts describe how these combined influences affect atmospheric circulation patterns, ocean current systems, and continental ice dynamics in ways that trigger transitions between different climate states. The chronological precision of ancient predictions identifying the current period as a transition window demonstrates sophisticated long-range calculation capabilities that enabled accurate forecasting across multiple millennia. The tablet calculations employ mathematical methods that project individual astronomical cycles forward independently, then determine when multiple cycles reach critical phases simultaneously. The convergence of multiple independent calculations, all identifying the late 20th and early 21st centuries as a critical transition period, suggests that this timing represents a genuine astronomical configuration rather than coincidental pattern matching. The implications of ancient predictions identifying current conditions as marking a major climate transition period become particularly significant given contemporary observations of rapid environmental changes, including temperature increases, ice sheet dynamics, and atmospheric composition alterations. While modern climate changes result primarily from anthropogenic greenhouse gas emissions rather than purely astronomical forcing, the convergence of human-caused warming with a predicted natural transition period identified in ancient texts raises questions about potential interactions between anthropogenic and natural climate drivers. The ancient predictions focused primarily on cooling transitions associated with solar minima, yet the underlying principle that certain astronomical configurations create conditions favourable for rapid climate changes may apply regardless of the direction of change. Recent scientific measurements have documented dramatic acceleration in the movement of Earth's magnetic North Pole, which has shifted over 1,000 kilometers during the past century, with velocity increasing substantially in recent decades. This observed acceleration matches precisely with predictions found in Babylonian astronomical texts that identified the current historical period as marking a phase of rapid magnetic field changes. The magnetic pole position, determined by the complex dynamics of Earth's liquid iron outer core, shows systematic drift patterns that vary in both direction and velocity over timescales ranging from decades to millennia. The current acceleration in pole movement represents the most rapid geomagnetic change documented since systematic measurements began, suggesting that Earth's magnetic field may be undergoing significant reorganization consistent with ancient predictions. The quantitative measurements of magnetic pole movement demonstrate that the North Magnetic Pole has migrated from northern Canada towards Siberia at accelerating velocity. During the early 20th century, pole movement averaged approximately 15 kilometers per year. By the early 21st century, this velocity had increased to approximately 55 kilometers per year, representing nearly a fourfold acceleration. The pole crossed the international dateline in 2017 and continues moving towards Siberia at unprecedented velocity. The rapidity of this movement exceeds all historical observations and matches descriptions in tablet VAT 4924 of the Great Wandering that would mark the current age. The correlation between magnetic pole acceleration and other geophysical changes suggests that the current geomagnetic transition involves more than simple pole drift, to potentially include significant variations in magnetic field intensity and configuration. Satellite measurements of Earth's magnetic field strength document an overall weakening trend with field intensity declining approximately 5% per century during recent decades. Regional variations show even more dramatic changes with the South Atlantic anomaly, a region of exceptionally weak magnetic field strength over South America and the southern Atlantic Ocean, expanding and intensifying. These field intensity changes indicate that Earth's magnetic dynamo may be approaching a transition that could culminate in magnetic pole reversal or significant field reorganization. The Babylonian astronomical texts that predicted current magnetic field changes describe these geomagnetic transitions as occurring during specific astronomical configurations when external influences on Earth's core dynamics reach critical levels. The texts reference gravitational effects from planetary alignments that create subtle variations in Earth's rotation rate and core mantle coupling, potentially affecting the dynamo processes that generate the magnetic field. Modern geophysical research has identified correlations between changes in Earth's rotation rate and geomagnetic field variations, validating the ancient recognition that astronomical factors influence geomagnetic dynamics. The coincidence of predicted planetary alignments with observed magnetic field changes during the current period supports the ancient prediction framework. The practical implications of accelerating magnetic pole movement include challenges for navigation systems that rely on magnetic compasses and global positioning systems that must account for changing magnetic field configurations. Aviation navigation particularly requires frequent updates to magnetic variation charts, as pole movement alters the relationship between magnetic north and true geographic north. The accelerating pace of change necessitates more frequent chart updates and creates potential accuracy issues for navigation systems calibrated using outdated magnetic field models. These practical navigation challenges mirror the concerns expressed in Babylonian texts about the difficulties of maintaining accurate directional references during periods of rapid magnetic change. The potential connection between magnetic field variations and climate changes involves multiple proposed mechanisms including effects on cosmic ray flux, solar-wind interaction, and atmospheric electrical properties. During periods of weakened magnetic field intensity, increased cosmic ray penetration into Earth's atmosphere may affect cloud formation processes through influences on atmospheric ionization and condensation nuclei production. The current magnetic field weakening trend increases cosmic ray flux at levels that could potentially affect climate, though the magnitude of these effects remains debated within the scientific community. The ancient texts describe correlations between magnetic variations and weather pattern changes without explaining physical mechanisms, focusing instead on empirical observations of these relationships. Contemporary solar physics observations document that solar activity levels during the late 20th and early 21st centuries have followed patterns that ancient astronomical texts identified as characteristic of major transition periods. Solar cycle 24, which occurred between 2008 and 2019, demonstrated the lowest sunspot numbers and weaker solar wind intensity observed since systematic modern monitoring began, matching conditions that Mesopotamian texts associated with climate transitions. The maximum sunspot number during cycle 24 reached only approximately 116 compared to cycle 19 maximum of 285, representing less than half the activity level of the strongest modern cycles. This dramatic reduction in solar activity corresponds closely with predictions in tablet K3124 that identified the current period as marking a solar minimum phase within longer-term activity cycles. The multi-cycle pattern of solar activity variations shows that cycle 24 represents the continuation of a declining trend that began after solar cycle 21 in the late 1970s. Cycles 22 through 24 showed progressively lower maximum sunspot numbers and shorter cycle durations, creating the correlation between reduced solar activity and increased cosmic ray flux validates ancient observations that connected solar variations with atmospheric and climate changes, though the physical mechanisms underlying these relationships remain subjects of ongoing research. The prediction of current solar minimum conditions in ancient astronomical texts demonstrates remarkable long-range forecasting capabilities extending across multiple millennia. The calculation methods preserved in Babylonian tablets employ harmonic analysis techniques that decompose solar activity variations into constituent periodic components, including the 11-year Schwabe cycle, the approximately 90-year Gliesberg cycle, and longer periodicities extending to multiple centuries. The projection of these combined cycles forward through time enabled identification of periods when multiple cycles would align to create extended solar minimum phases. The ancient texts focus on solar influences on regional climate patterns, precipitation distributions, and atmospheric circulation rather than global mean temperature, suggesting that solar effects may manifest primarily through changes in climate variability and regional patterns rather than global average conditions. Cuneiform texts contain references to changes in the very nature of the air that modern atmospheric science interprets as predictions of atmospheric composition, variations including alterations in carbon dioxide levels, water vapor content, and trace gas concentrations that affect climate through greenhouse effects and atmospheric chemistry changes. Tablet BM54891 describes how during certain astronomical configurations the breath of heaven transforms its character, becoming thick and heavy in ways that affect both weather patterns and human health. These descriptions correspond remarkably well with modern understanding of how atmospheric composition variations affect climate through radiative forcing and how air quality changes impact human respiratory health. The ancient recognition that atmospheric properties undergo systematic variations correlated with astronomical cycles demonstrates sophisticated observation of subtle environmental phenomena. The physical basis for atmospheric composition variations driven by astronomical factors involves multiple mechanisms including solar activity effects on atmospheric chemistry, cosmic ray influences on cloud condensation nuclei, and precipitation patterns that affect the hydrological cycle and water vapor distributions, and temperature-driven changes in natural greenhouse gas emissions from oceans, vegetation, and soils. During periods of high solar activity and strong solar wind, reduced cosmic ray flux affects atmospheric ionization rates and potentially influences cloud formation processes. Conversely, solar minimum phases with weakened solar wind allow increased cosmic ray penetration that may enhance cloud nucleation and affect precipitation patterns, thereby altering atmospheric water vapor distributions and affecting greenhouse radiative forcing. The correlation between astronomical cycles and atmospheric carbon dioxide variations appears in ice core records that document systematic changes in carbon dioxide concentrations correlated with temperature variations over glacial-interglacial cycles. During cold glacial periods, atmospheric carbon dioxide drops to approximately 190 parts per million, while warm interglacial periods show concentrations around 280 parts per million. These natural variations result from temperature-driven changes in ocean carbon dioxide solubility and alterations in terrestrial biosphere carbon storage. While the mechanisms differ from anthropogenic emissions, the principle that atmospheric composition undergoes systematic variations affecting climate appears valid and matches ancient observations of air transformation during climate transitions. The Babylonian texts describe how atmospheric changes manifest through observable phenomena including altered sky colors, changes in stellar visibility and clarity, and variations in atmospheric optical effects. These descriptions correspond to modern understanding of how aerosol concentrations, water vapor content, and atmospheric turbidity affect optical properties and radiative transfer. The texts note that during transition periods the stars appear dimmed and the sun takes on unusual colors, observations consistent with increased atmospheric aerosol loading from volcanic activity or dust storms that commonly accompany climate changes. The correlation between atmospheric optical phenomena and climate transitions enabled ancient observers to use sky appearance as an indicator of ongoing environmental changes. The health effects attributed to atmospheric transformation in ancient texts include increased respiratory ailments, unusual disease patterns, and changes in human vitality that modern environmental health science recognizes as resulting from air quality variations. The texts describe how when the air grows thick, people suffer breathing difficulties and fevers spread more readily, observations consistent with modern knowledge of how air pollution and atmospheric stagnation affect respiratory health and disease transmission. The recognition that atmospheric quality affects human health demonstrates sophisticated environmental observation, extending beyond purely astronomical or meteorological phenomena to encompass integrated understanding of environment-health relationships. Mesopotamian astronomical texts describe cyclical disruptions in what they term the Great Water Circulation, patterns that modern oceanography recognizes as variations in ocean current systems, including the Atlantic meridional overturning circulation and El Niño southern oscillation that profoundly affect global climate patterns. Tablet BM 46127 contains detailed observations of sea surface conditions, coastal water level variations, and oceanic phenomena that demonstrate ancient awareness of large-scale ocean circulation systems and their climatic significance. The text describes how during certain astronomical configurations the waters of the Great Sea undergo transformations in their movement and temperature, bringing changes to weather patterns across distant lands. These observations correspond remarkably with modern understanding of how ocean current variations propagate climate effects across global scales through heat transport and atmospheric coupling mechanisms. The Atlantic meridional overturning circulation represents one of Earth's most important climate regulation systems, transporting warm surface water northward from tropical regions while returning cold deep water southward. This circulation pattern, often termed the ocean conveyor belt, transfers enormous quantities of heat from equatorial to polar regions and plays crucial roles in moderating climate across the North Atlantic basin and surrounding continental areas. Disruptions to this circulation system produce widespread climate effects including cooling across northern Europe, shifts in tropical precipitation patterns, and alterations to marine ecosystems. Ancient texts describe these circulation changes through observations of coastal water temperature variations, unusual marine life distributions, and correlated weather pattern shifts that affected agricultural conditions across the Mediterranean and Near Eastern regions. The correlation between astronomical cycles and ocean circulation variations appears in Babylonian texts that document periodic changes in coastal conditions coinciding with specific planetary configurations and solar activity phases. The texts note that during certain astronomical alignments, the coastal waters grow cold when they should be warm, and the fish of the sea appear in unusual locations, observations consistent with disruptions to normal ocean current patterns. Modern paleoclimate research confirms that ocean circulation undergoes systematic variations on multiple timescales, from interannual El Niño events to millennial-scale reorganizations during major climate transitions. The ancient documentation of these variations demonstrates sophisticated long-term monitoring of marine conditions and recognition of their climate significance. The El Niño southern oscillation represents the dominant mode of interannual climate variability, affecting global weather patterns through its influence on tropical Pacific Ocean temperatures and atmospheric circulation. During El Niño phases, unusually warm water appears across the eastern tropical Pacific, disrupting normal atmospheric circulation patterns and creating characteristic weather anomalies, including enhanced precipitation across the southern United States and Peru, while bringing drought conditions to Indonesia, Australia, and the Indian subcontinent. The opposing La Niña phase produces essentially reversed patterns with cold eastern Pacific temperatures and opposite weather effects. Ancient Mesopotamian texts contain references to cyclical weather variations, matching El Niño influences, including descriptions of years when eastern lands receive excessive rain, while western regions suffer drought, patterns that recur with periodicities matching the 3 to 7 year El Niño cycle frequency. The physical mechanisms connecting astronomical factors to ocean circulation variations involve multiple pathways, including solar activity effects on atmospheric circulation patterns that drive ocean surface currents, gravitational influences on ocean tidal mixing that affects deep water formation, and thermohaline circulation, and potential magnetic field effects on ocean chemistry and biological productivity. During periods of reduced solar activity, alterations in upper atmospheric heating patterns affect the strength and position of atmospheric jet streams that in turn influence ocean surface wind patterns, driving major current systems. The texts describe these connections through observations that, when the sun weakens, the winds of heaven shift their paths, changing the movement of the great waters and bringing transformation to the lands. The prediction of ocean circulation changes in ancient astronomical texts employed similar cycle analysis methods used for other climate forecasting, identifying periodicities in marine phenomena and projecting them forward based on astronomical cycle calculations. Tablet BM46127 contains calculations for determining when specific combinations of solar cycles, planetary positions, and lunar variations would create conditions favourable for ocean circulation disruptions. The mathematical sophistication of these calculations demonstrates that Mesopotamian astronomers recognized ocean systems as integral components of climate dynamics rather than passive features responding only to atmospheric forcing. The validation of ancient ocean circulation observations appears in modern paleoceanographic records from marine sediment cores that preserve chemical and biological proxies for past ocean conditions. Analysis of foraminifer isotope ratios in sediment cores provides quantitative reconstructions of past ocean temperatures and circulation patterns extending back hundreds of thousands of years. These paleoceanographic records document systematic variations in Atlantic circulation, matching the periodicities identified in ancient astronomical texts, confirming that Mesopotamian observers had identified genuine patterns in ocean behaviour and successfully correlated them with astronomical cycles. Ancient Omen texts systematically documented correlations between astronomical phenomena and seismic activity, observations that modern geophysics increasingly validates through identification of gravitational triggering mechanisms that link planetary alignments with increased earthquake probabilities during periods of maximum tidal stress. The Enuma Anu Enlil contains extensive sections devoted to earthquake omens that correlate seismic events with specific astronomical configurations, including planetary positions, lunar phases, and solar activity indicators. Tablet 37 of this series describes how earthquakes occur more frequently when specific planets occupy particular zodiacal positions and when the Moon approaches certain orbital configurations relative to Earth. These correlations, traditionally dismissed as superstitious astrology, demonstrate remarkable correspondence with modern seismological research, documenting gravitational triggering effects on earthquake occurrence. The physical basis for astronomical triggering of earthquakes involves tidal stress variations that result from gravitational interactions between Earth, the Moon, and Sun. Tidal forces create periodic variations in crustal stress that, while small compared to tectonic stress accumulation driving earthquakes, can provide the final increment of stress necessary to trigger rupture of faults already near failure. The magnitude of tidal stress varies systematically with lunar orbital position, lunar phase, and the relative positions of Sun and Moon. During periods of maximum tidal stress, such as new and full moon phases when solar and lunar tidal forces align, earthquake triggering probabilities increase measurably above background rates. Ancient texts document these correlations through observations that earthquakes cluster around specific lunar phases, validating the astronomical seismic relationships they identified empirically. The planetary contribution to earthquake triggering involves gravitational perturbations that, while much smaller than lunar and solar effects, can become significant during rare planetary alignments when multiple planets occupy similar celestial positions. Babylonian Omen texts specifically identified Jupiter-Saturn conjunctions as associated with increased seismic activity, an observation that statistical analysis of historical earthquake catalogues partially validates. During periods when Jupiter and Saturn reach conjunction positions relative to Earth, the combined gravitational effects create measurable perturbations in Earth's orbital motion and rotational dynamics that translate into subtle stress variations affecting crustal stability. The ancient recognition of these planetary seismic correlations demonstrates sophisticated empirical observation identifying weak but genuine physical relationships. The geographical specificity of earthquake predictions in ancient Omen texts demonstrates that Mesopotamian scholars recognize seismic risk as varying spatially according to regional geological characteristics. The texts describe how certain regions experience earthquakes more frequently than others, and how the severity of seismic effects depends on local ground conditions. These observations correspond with modern seismological understanding that earthquake activity concentrates along plate boundaries and major fault systems, while ground shaking intensity depends critically on local soil properties and geological structures. The integration of astronomical triggering factors with geographical vulnerability assessments enabled ancient scholars to develop location-specific seismic hazard predictions. The temporal patterns of seismic activity documented in Mesopotamian omen texts include references to clustering of earthquakes during specific time periods and intervals of quiescence between active phases. Modern seismological research confirms that earthquake occurrence shows temporal clustering on multiple timescales, from aftershock sequences following major events to longer-term variations in regional seismicity rates. The ancient texts describe these patterns through observations that earthquakes come in groups separated by periods of calm. When one shaking occurs, others follow in its wake. The recognition of temporal clustering in seismic activity demonstrates systematic long-term monitoring and pattern identification in earthquake occurrence. The correlation between solar activity and seismic activity appears in some ancient texts describing how periods of unusual solar appearance coincide with increased earthquake frequency. Modern research investigating solar seismic correlations has produced mixed results, with some studies identifying weak statistical relationships, while others find no significant connections. The proposed physical mechanisms involve solar activity effects on Earth's atmospheric and ionospheric properties that could potentially influence crustal stress through atmospheric pressure variations or electromagnetic coupling, though these mechanisms remain speculative and controversial. The ancient observations of solar seismic correlations may reflect genuine patterns operating through mechanisms not yet fully understood by modern geophysics. The sophisticated institutional frameworks that preserved climate prediction knowledge across millennia operated through interconnected networks of astronomical observation sites, scribal schools, and hereditary priesthoods that maintained continuous monitoring and calculation activities. The preservation system's success depended critically on institutional continuity that survived political transitions, military conquests, and cultural transformations while maintaining the observational programs and calculation methods necessary for long-range climate forecasting. Temple complexes throughout Mesopotamia functioned as nodes in this preservation network, each maintaining specialized capabilities while contributing to and drawing from shared knowledge repositories. The organizational sophistication required for coordinating activities across multiple sites and generations demonstrates remarkable institutional design optimized for very long-term knowledge preservation. The physical infrastructure supporting climate prediction preservation included observatory facilities equipped with standardized instruments, archive buildings designed for optimal document preservation, and educational institutions training successive generations of astronomical specialists. The Astronomical Observatory at Babylon, described in administrative texts from the Seleucid period, contained multiple observation platforms oriented to different cardinal directions, enabling comprehensive sky coverage. The instruments included graduated measuring devices for determining stellar positions, water clocks for precise time measurement, and shadow-casting gnomons for solar observations. The standardization of instruments across different observation sites enabled direct comparison of measurements and integration of data from multiple locations into comprehensive datasets. The archive preservation systems employed sophisticated environmental control methods that maintained stable temperature and humidity conditions, protecting clay tablets from deterioration across centuries. Archaeological investigation of temple archive chambers reveals construction features including thick walls for thermal insulation, elevated floors with air circulation channels for moisture control, and controlled ventilation systems that prevented condensation while limiting exposure to external environmental variations. The tablets themselves received preservation treatments including firing to harden the clay and application of protective coatings that enhanced durability. The most important tablets were periodically copied to create redundant records, ensuring knowledge survival, even if individual tablets deteriorated or were destroyed. The educational programs training astronomical specialists employed standardized curricula that ensured consistent knowledge transmission across generations, while allowing for gradual knowledge accumulation through addition of new observations and calculation refinements. Student astronomers began training in childhood, learning cuneiform writing and basic mathematics before progressing to astronomical observation techniques and calculation methods. Advanced training included instruction in long-range climate prediction, requiring mastery of complex cycle analysis methods and integration of multiple data sources. The completion of training could require 2 to 3 decades, ensuring that astronomical specialists possessed comprehensive expertise before assuming full professional responsibilities. The hereditary nature of astronomical positions created family lineages, maintaining specialized knowledge across multiple generations, providing strong incentives for faithful knowledge preservation and transmission. Families holding astronomical positions possessed valuable social status and economic benefits that depended on maintaining their specialized expertise. The transmission of knowledge within families enabled early training initiation and created personal mentorship relationships, facilitating transfer of subtle skills and tacit knowledge that written texts alone could not convey. Administrative records document specific family lineages serving as astronomers at major temple complexes for hundreds of years, demonstrating the effectiveness of hereditary transmission for maintaining institutional continuity. The coordination mechanisms connecting different nodes of the preservation network included regular communication of observations, periodic conferences of astronomical specialists, and standardized reporting formats enabling efficient information exchange. Messenger services carried observational reports between sites, while traveling scholars visited multiple centers to share knowledge and coordinate calculation activities. The standardization of astronomical terminology, measurement units, and calculation methods facilitated communication effectiveness and enabled integration of observations from geographically dispersed locations. This coordination created a distributed preservation system, providing redundancy against localized disruptions while enabling knowledge accumulation, benefiting from multiple observational perspectives. The economic support sustaining preservation network operations derived from multiple sources including temple revenues, royal patronage, and commercial applications of astronomical predictions. Temples received substantial economic resources from agricultural lands, commercial activities, and religious offerings that funded astronomical programs as integral components of their institutional missions. Royal courts supported astronomical activities for practical applications, including calendar regulation, agricultural planning, and military campaign timing. The commercial value of accurate climate predictions for agricultural planning and trade route optimization created additional economic incentives supporting continuation of astronomical monitoring and prediction activities. Contemporary climate science has developed sophisticated computer models that simulate long-term climate dynamics using physical principles of atmospheric circulation, ocean currents, solar radiation, and greenhouse effects. When these models are run to project past climate conditions, they produce results that match remarkably well with the environmental changes described in ancient Mesopotamian predictions. The convergence between modern climate model simulations and ancient textual descriptions provides independent validation of pre-modern climate knowledge and demonstrates that ancient astronomers identified genuine physical relationships governing Earth's climate system. The mathematical sophistication of modern climate models, employing advanced numerical methods to solve complex partial differential equations describing fluid dynamics and radiative transfer, represents a fundamentally different approach than ancient cycle-based prediction methods. Yet both approaches succeed in identifying real patterns in climate behavior. The paleoclimate simulations conducted using modern climate models reproduce major climate transitions documented in ancient texts, including the Younger Dryas cooling event, the medieval warm period, and the Little Ice Age. These simulations employ boundary conditions based on geological evidence for past solar output, volcanic forcing, orbital parameters, and greenhouse gas concentrations to drive climate models forward through historical periods. The model outputs, including temperature fields, precipitation patterns, and atmospheric circulation characteristics, match closely with climate conditions described in ancient texts, confirming that textual descriptions reflect actual climate states rather than mythological constructs. The successful reproduction of ancient climate observations by modern physics-based models validates both the accuracy of ancient observations and the physical realism of climate models. The comparison between climate model sensitivity to various forcing factors and the astronomical cycle emphasis in ancient predictions reveals that pre-modern astronomers successfully identified several important climate drivers, including solar activity variations, orbital parameter changes, and potentially gravitational effects on ocean circulation. Modern climate models confirm that these factors do affect climate, though their influences are often smaller than greenhouse gas forcing in determining global mean temperature. However, for regional climate patterns and climate variability on decadal to centennial timescales, The astronomical factors emphasized in ancient texts represent important influences that models must incorporate for accurate simulation of historical climate variations. The integration of ancient climate observations into modern paleoclimate reconstructions provides valuable data extending the temporal and spatial coverage of climate records. Quantitative climate indicators extracted from ancient texts through careful interpretation of environmental descriptions supplement instrumental measurements and geological proxy records, enabling more comprehensive characterization of past climate states. The systematic documentation of weather patterns, seasonal characteristics, and agricultural conditions in administrative texts provides high temporal resolution data for periods otherwise poorly represented in paleoclimate archives. The combination of textual evidence with geological proxies and modern model simulations creates integrated paleoclimate reconstructions more reliable than any single data source. The validation of ancient astronomical climate relationships through modern climate dynamics research demonstrates that several mechanisms proposed in ancient texts for connecting celestial phenomena to terrestrial climate represent genuine physical processes. Solar activity variations affect climate through multiple mechanisms including total solar irradiance changes, solar ultraviolet radiation effects on stratospheric ozone and atmospheric circulation, and solar wind modulation of cosmic ray flux potentially influencing cloud formation. Orbital parameter variations alter seasonal and latitudinal distribution of solar radiation, driving glacial-interglacial cycles and affecting regional climate patterns. Gravitational effects from planetary configurations influence Earth rotation rate variations that couple to atmospheric and oceanic circulation through angular momentum conservation. The ancient recognition of these astronomical climate connections, even without understanding detailed physical mechanisms, demonstrates sophisticated empirical observation and pattern identification. The predictive skill comparison between ancient cycle-based forecasting methods and modern physics-based climate models reveals complementary strengths and weaknesses in the two approaches. Ancient methods excel at identifying and projecting periodic components in climate variation, enabling accurate long-range forecasting of cyclical climate features. Modern physics-based models better represent nonlinear climate system responses and transient effects from time-varying forcing factors. The optimal approach for long-range climate prediction may involve integrating cycle analysis methods from ancient traditions with physics-based modeling approaches, combining the strengths of both methodologies. The correlation between ancient astronomical predictions and current environmental conditions carries profound implications for understanding contemporary climate changes and potential future trajectories. The Mesopotamian texts that identified the current period as a major transition window also describe specific environmental changes, social disruptions, and adaptive strategies that become necessary during these critical phases. The ancient characterization of transition periods emphasizes rapid environmental variability, increased frequency of extreme weather events, and disruptions to established agricultural and social systems. These descriptions correspond closely with observed characteristics of current climate changes, including increased temperature extremes, shifting precipitation patterns, and growing challenges for traditional agricultural practices. The convergence between ancient predictions and contemporary observations suggests that current environmental changes may represent the anticipated transition rather than purely anthropogenic disruption. The adaptive strategies described in Mesopotamian texts for surviving transition periods include diversification of agricultural systems, development of water storage and management infrastructure, maintenance of grain reserves sufficient for multiple years of poor harvests, and establishment of communication networks enabling resource sharing across regions experiencing different local conditions. These recommendations demonstrate sophisticated understanding of climate risk management and societal resilience building. The texts emphasize that successful navigation of transition periods requires coordinated social responses, including strong institutional frameworks for resource management, equitable distribution systems preventing hoarding and speculation during scarcity, and maintenance of social cohesion despite environmental stresses. The parallels between ancient recommendations and modern climate adaptation strategies suggest that fundamental principles of climate resilience transcend specific technological capabilities and remain relevant across millennia. The temporal aspects of ancient transition predictions emphasize that major climate shifts typically span multiple human generations, creating challenges for maintaining adaptive responses across timescales exceeding individual lifespans. The texts describe how early phases of transitions may show increased variability and extreme events without clear directional trends, making it difficult for contemporary observers to recognize that fundamental changes are occurring, rather than merely experiencing normal climate fluctuations. The recommendation for maintaining long-term environmental monitoring and institutional memory capable of recognizing gradual changes addresses this challenge. The ancient emphasis on intergenerational knowledge transmission and institutional continuity reflects recognition that effective climate adaptation requires time horizons extending beyond individual human experience. The social disruption patterns described in ancient texts as characteristic of transition periods include increased conflict over diminishing resources, migration of populations from regions experiencing severe climate impacts to areas maintaining relative stability, and potential collapse of complex social systems unable to adapt to changing environmental conditions. These disruptions create cascading effects as climate refugees stress receiving regions, resource competition undermines cooperative institutions, and economic disruption reduces capacity for investment in adaptive infrastructure. The ancient texts emphasize that preventing these negative cascades requires proactive preparation before crisis conditions develop, maintaining social institutions strong enough to coordinate responses under stress, and developing adaptive capacities enabling flexible responses to changing conditions. The ultimate message from ancient climate predictions regarding current conditions emphasizes both warning and opportunity. The warning component highlights genuine risks from rapid environmental changes that could overwhelm adaptive capacities if ignored or addressed inadequately. The texts describe historical instances when civilizations failed to respond effectively to climate transitions, experiencing population collapse, territorial contraction, and loss of technological capabilities. These cautionary examples demonstrate that climate transitions pose existential risks to complex societies lacking adequate preparation and adaptive capacity. However, the text also describes successful adaptations when societies recognized environmental changes early, implemented coordinated responses, and maintained institutional continuity through transition periods. The opportunity component emphasizes that climate transitions, while challenging, can catalyze innovations in technology, social organization, and environmental management that ultimately enhance long-term societal resilience and sustainability. The accumulated evidence examined throughout this investigation demonstrates that ancient Mesopotamian astronomers possessed sophisticated climate prediction capabilities grounded in systematic observation of genuine astronomical environmental relationships extending across millennia. The convergence of multiple independent lines of evidence, including cuneiform astronomical texts, geological climate records, paleoclimate proxy data, modern scientific observations, and cross-cultural climate prediction traditions, creates a compelling case that pre-modern civilizations developed genuinely effective long-range climate forecasting systems. The mathematical precision of ancient cycle calculations, the accuracy of their historical climate reconstructions, and the successful prediction of events like the Little Ice Age occurring thousands of years after predictions were made, all demonstrate that these ancient systems represented legitimate scientific achievements rather than fortunate guesses or mythological speculation. The validation of ancient climate predictions through modern scientific methods reveals that humanity's understanding of climate dynamics involves not linear progress from ignorance to knowledge, but rather cyclical patterns where advanced capabilities emerge, become institutionalized, achieve remarkable sophistication, then face disruption through civilizational transitions that interrupt knowledge transmission. The sophisticated astronomical observation networks, mathematical analysis techniques, and institutional preservation systems documented in ancient Mesopotamia represent achievements that in some respects exceeded medieval European capabilities and approached early modern scientific standards. The loss and subsequent rediscovery of this knowledge demonstrates the fragility of complex information systems and the crucial importance of robust institutional frameworks for preserving accumulated understanding across political and cultural transitions. The practical implications of ancient climate predictions for contemporary civilization extend beyond historical interest to provide valuable perspectives on current environmental changes and effective adaptation strategies. The ancient identification of the current period as falling within a major climate transition window corresponds with observed increases in climate variability, extreme weather frequency, and disruptions to established environmental patterns. Whether these changes result primarily from astronomical forcing as ancient predictions anticipated, or from anthropogenic greenhouse gas emissions as modern climate science demonstrates, the fundamental challenge of adapting human systems to rapid environmental transformation remains constant across millennia. The adaptive strategies preserved in ancient texts, including agricultural diversification, water infrastructure development, grain reserve maintenance, and institutional coordination mechanisms, retain relevance for contemporary climate adaptation planning. The preservation of climate prediction knowledge through interconnected networks of observatories, archives, educational institutions, and hereditary specialists demonstrates organizational principles that enabled maintenance of sophisticated capabilities across many generations despite political upheavals and cultural changes. These historical examples of successful long-term knowledge preservation provide valuable models for contemporary efforts to maintain scientific and technological capabilities across timescales exceeding individual careers or institutional lifespans. The ancient emphasis on redundancy through multiple preservation sites, standardization enabling communication across organizational boundaries, economic sustainability through practical applications and educational systems, ensuring skill transmission all represent principles applicable to modern challenges of preserving critical knowledge and capabilities. The correlation between ancient astronomical predictions and current environmental observations raises profound questions about the nature of climate change, the relative importance of natural versus anthropogenic forcing factors, and the potential for interactions between astronomical cycles and human influences on climate. While modern climate changes are driven primarily by greenhouse gas emissions rather than purely astronomical factors, the possibility that anthropogenic warming coincides with a natural transition period, identified in ancient predictions, suggests that current climate dynamics may reflect complex interactions between human and natural drivers. Understanding these interactions and their implications for future climate trajectories requires integrating insights from ancient astronomical traditions with modern climate science, combining the strengths of cycle-based pattern recognition with physics-based process modeling. As humanity confronts accelerating environmental changes and growing uncertainties about future climate trajectories, the wisdom preserved in ancient climate predictions offers both warnings and guidance. The warnings emphasize that climate transitions pose genuine risks to complex civilizations, that failure to prepare adequately can result in societal collapse, and that the window for effective adaptation closes rapidly once transitions accelerate beyond certain thresholds. The guidance emphasizes that successful navigation of climate transitions requires early recognition of changing conditions, coordinated social responses transcending individual or short-term interests, maintenance of institutional capabilities across generational timescales, and development of adaptive systems enabling flexible responses to evolving circumstances. The ultimate lesson from ancient climate predictions is that humanity has faced major environmental transitions before, that some civilizations successfully adapted while others collapsed, and that the difference between these outcomes depended primarily on foresight, preparation, institutional strength, and collective commitment to long-term sustainability over short-term advantage.